We have Origin and Fate of Atmospheric Moisture over Continents, an article by Rudy van der End, Hubert Savanet, Bettina Schäfli and Susan Steele-Dunn that was published in Water Resources Research in 2010. And as the title suggests, we're going to talk about cycling of atmospheric moisture, rainfall and evaporation. Where does it come from and where does it go to? As any good article, it starts with a simple why. Why would we be interested in how moisture moves through the atmosphere over the Earth? It's basically because of the magnitude of soil moisture, moisture recycling is an important indicator for this, how things will change with the climate if you change land use. If you change the surface area of the land, something will happen to the evaporation, and that may or may not have a downstream effect on precipitation. What is moisture recycling? Moisture recycling is really how much of the water that evaporates at a certain point returns back as precipitation at that same point or in that same region. And early thoughts from the last centuries basically saying, well, the rain follows the plow. If you start increasing the evaporation from a certain area, definitely the precipitation in the same area has to increase. But then with the Dust Bowl of the 1930s, this way of thinking was abolished, and a lot of studies started looking into this question. And it's obvious why. Probably it's very important to understand what local effects land use change may have. But the conclusions of all these studies did not really converge, and there were several reasons for that. And in this article, basically, after a careful review of all these studies, they say, well, basically there's a lack of consensus on how important moisture recycling is. But it's also because everybody uses different methods, different assumptions, and different definitions. And part of the problem there is that, people were always interested in a certain area. So if something evaporates in, let's say, the Mississippi Basin, how much of that returns as rainfall in that same Mississippi Basin? And immediately jumps into mind is that, this must be scale dependent, because if you look at a very large area, let's say we take the whole Earth, everything that evaporates eventually will rain back to the Earth, precipitate on the Earth. If, however, you look at a very small place, maybe your backyard, whatever evaporates there probably is very unlikely to precipitate there again. It will probably precipitate a little bit downwind. And so the scale dependency immediately jumps into mind, but also exactly what shape does the area have, etc., etc. Now, that brings us immediately to the innovation of this paper. It's highlighted here. Is for the first time we have global maps where to show where rainfall that falls over the continents originates from. Does it originate also from the continents, or does it mainly originate from the oceans? That for the first time then allows you to see in one go, is what areas are important and what should we worry about, which areas would be affected if you change land use and land cover in a certain area. So that's the real innovation that we have for the first time, a global look. Now, how do they do that? First, a couple of definitions, and you can argue about them for a long time, but basically they work fine in the way they show you. They will show what needs to be shown, and throughout you will see this formulation, which is also highlighted here in equation number 1. And basically, what it says, for a certain area, with a certain size A and a certain shape delta, at a certain time t, in a certain place, coordinate within that area, we can see what the rainfall P is as a sum of two contributions, if you want. One, that part of the rain that originated within that same area, within that same area and shape, and part of it that's affected from outside that area, PA in this case, and these two together will be the total rainfall. Very clear. And then we can say, what is then the regional precipitation recycling ratio? Well, that's defined then a little bit lower, which is basically the rainfall that originated from that area divided by the total rainfall. Similarly, for the evaporation, we can also see that a part of the evaporation will return to the same region as rainfall. That's ER in this case, and the other part will be affected away. and will probably precipitate somewhere else. This is where how we define our evaporation. Now, when you average this, whatever will recycle from the evaporation into rainfall will be the same as the rainfall that was recycled from evaporation within that region, assuming, as they say, no substantial change in atmospheric soil moisture over a year. Now, you probably also have to take other storage changes actually into account that might be terrestrial in origin. But in general, because the fluxes are very large, it's a very sensible sensible assumption that over a long period, change in storage is negligible compared to the total fluxes integrated over that same period. That brings us then to the recycling ratio of evaporation, which is the amount of evaporation from a certain region that precipitates in that same region divided by the total evaporation from that region. Now, in words it's all very difficult, but as you see in formula it's very clear. Now this brings us back, of course, immediately to what it was said already here in the highlighted part. It's very difficult if you look at one region, what the importance then is of this recycling for continental moisture feedback, because it depends on the size, depends on the exact patterns and all of the area, and etc. etc. So what did they use here then to overcome that problem? All these arguments are always about it's important, it's not important. Well, what they now do, instead of saying, okay, we take this region, we say, okay, we take all the continental areas of the world as the mother region, so as an origin of our rainfall. And that we can go through exactly the same as we went before. We say, okay, the rainfall consists of a part that originates from the continents and a part that originates from the oceans, is shown here in equation 6. And the same for evaporation. Part of the evaporation consists of evaporation that comes from the oceans, and part of it comes from the continent. This then also leads to a new definition of continental evaporation recycling ratio, which is the amount of evaporation that evaporates from the continents and recycles as precipitation divided by the total amount of evaporation from the continents. The data they used are ERA interim reanalysis data, the ECMWF data. In a way, that's the best data set we have. It comes from the European Center for Mid-Range Weather Forecasts, but it's not really a weather forecast. It's really a reanalysis. It's looking back. It's like, okay, given our models, given our observations, what was the atmospheric circulation over the past 10 years or so? And so it's really the best idea that we have about how air and moisture moved through the atmosphere and around the globe. For this study, they used the period 1999 to 2008. They actually had one extra year, which they used as sort of like a spin-up period, and then they used the 10 years that follows as sort of like the benchmark area. Now, here's in the next page, then you see an important map. We'll come back to that later, but just quickly, you see that when you just look at the circulation patterns of moisture, the bigger the air, the more moisture is moving around. You see these general patterns, a lot of moisture moving at the equator from east to west, and at more moderate latitudes, it moves in the other direction. And you also see some highlights that we'll come back to later, Northern America, Amazonia, and Africa. Now, it's still quite evolved in what you then have to do. Is, you have to basically, what do you mean by how the moisture moves through the air? Well, basically, for a given area, you look at what the change in atmospheric moisture storage is. You add to that the change in advection or in a certain direction. If we have a square pixel in this case in the x direction, plus the advection which takes place in the y direction, and what that basically gives you the change in storage over your area, and that has to be equal to the evaporation minus the precipitation. It's just a water balance for a part of the atmosphere. In this case, a square pixel with x going into a certain direction and y in the other, maybe east-west for x and north-south for y. Now, how do they do that then from the model? It's a bit becomes a little bit more technical here, but basically they integrate over the whole areas, the fluxes that come into this pixel. You see u, which is the wind speed in a certain direction. Q is the amount of water that comes with that wind speed, and they integrate it over from the pressure of 0 at the top of the atmosphere to atmospheric pressure, which is at the bottom of the atmosphere. That is equal to these convergent terms that you saw in the previous in equation number 11. Now, this is a lot of work, as we will see in a little bit, but it can be done. Instead of looking at one pixel, you could also just look at a whole region, and the same equations hold. It's just instead of having a simple x and y, you would have a more complicated shape. Then finally, what they do is an important assumption. Is actually the only real important assumptions that they make, and the only thing you could argue about if you really have to is like, well, in our approach, we assume the moisture in the atmosphere is well mixed. That is to say, is that if the moisture in the atmosphere has a certain origin, maybe 10% comes from the continent, then we think that whatever rains down from that over that same area also has 10% origin. So you can say, well, immediately all the moisture that evaporates somewhere is mixed throughout the atmosphere, and so whatever forms in terms of precipitation must have the same constitution. Now, again, for a very small part, that is not such a good assumption, but at global scales, for the global patterns and the global ratios that we will see, I think it's a fine assumption. And it's actually not even, you could also do a much more complicated one and do the analysis for each pressure layer if you want, but that would make it basically untractable from a computational point of view, and probably would not change much in the final outcome, as we will see a little bit later. So you do that for rainfall, and you do that for evaporation, and then you calculate basically here what the recycling ratio is in a certain area over a certain period. And you see that here, just the sum. Here's this assumption. As you see, a certain amount of the moisture in the atmosphere comes from the continents. That you divide by the total moisture in the atmosphere, that you multiply with the precipitation at a certain place in time, that you integrate over the whole time, that you divide by the whole precipitation over that same period to see how much of the rainfall originates from outside the area. Then there's a lot of work, because you have to basically run your whole model for each pixel that you have. So that's not a simple thing. That's why you also don't want to make it much more complicated than that. One disadvantage of the reanalysis data is that there is such a thing as a small error, because they don't maintain the water balance. They optimally combine observations and model, but that doesn't mean that they also maintain the water balance. So there's a small error here, and basically you assume that whatever that error is does not affect then the recycling patterns as will be calculated in this paper. Then we come to really what is the core of this paper, and it's the results, of course, that's mainly shown in these pictures here. And here you see figure 3, and it's a very interesting one. Actually, we should go back to the first figure that I showed before. But just quickly, you see that close to the coast and in accordance with the general circulation patterns, you see that the recycling ratio, the precipitation recycling ratio, increases when you go inland. Basically, the precipitation recycling ratio for the continents runs from 0 to 1. 0 means none of the rain that falls in that area originated from the continent, whereas a continental precipitation recycling ratio of 1 means that all the rainfall that falls on that place originated as evaporation from the continent somewhere. And we assume, and also when you look at the same pattern, at the patterns, that whatever evaporated, let's say on the Eurasian landmass, probably also precipitated there. Of course, the method also would allow for some drops from to arrive there from Australia, but given the general precipitation patterns, that's unlikely to happen. There's also, of course, then the average continental evaporation recycling ratio, and that sort of shows a mirror-like image, or a slightly different image. It shows that where the water evaporates, how much of the water that evaporates also precipitates back on the continent. And you see, for example, the north coast of South America, Guyana and Amazonia, that almost all the water that evaporates there rains back on the continent. Similarly, for East Africa, you see that a lot of the moisture there rains back somehow on the continents. And if we can flip back quickly to the picture showing all the main moisture recycling patterns, or the moisture cycling patterns, I should say. All the arrows, the bigger the arrow, the more moisture is moving. You see again the east to west around the equator, but at certain points that sort of blocked. For example, at the Andes, the moisture there just does not get over the Andes, and it's kind of stuck. Similarly, there's very little transport over the Himalayas, and even the Rockies here. You see that a lot of the moisture coming in from the Pacific Ocean does not really make it into the North American continent, and that most of the moisture that falls, for example, over the United States does not come from the Pacific, but comes from the Gulf of Mexico. So just by combining looking at this image of this general circulation patterns and at these result pictures showing these large patterns over the Earth, you can really come to very meaningful interpretations, as they also state here. And you should really look at them together, and then you really start understanding, like, oh, this is how this all sort of works in the Earth. Now, the little points that I already picked out from the pictures, it's also here in the words, and it shows that moisture recycling, continental moisture recycling, is very interesting in North America, the Amazon, and Africa, and also in the Eurasian, well, continental landmass, if you want. It seems, as they say, that it's difficult for moisture to leave this area. Not much comes over these large mountain chains like the Andes or the Himalayas, and even the rift, which is not that in East Africa, which is not that much of a blockade, you would say, seems to function a little bit as a blockade for the moisture cycling through the atmosphere around the globe. The things that need to be pointed out: South America, especially where the pattern, where the evaporation from the Guyanas and the northern Amazon region, is basically the origin for this all the rainfall in the Rio de Plata basin, the third largest river in the world. It all comes from that same continent. It does not go over the Andes. It's also clear that the Indian Ocean is the source of water for East Africa. A lot of the water that evaporates in East Africa ends up and on the continents again, but you can also see, when you combine these different images, that part of the Sahel, for example, also gets some of its water from the Mediterranean and the Gulf of Benin, or the South Atlantic Ocean. And that recycling is important. 50 to 60% is of the rainfall in Africa originates from the continent. Perhaps the most striking one is China, where northern China, not so much tropical China, but the North China Plain, Beijing, etc., where only 10 to 20% of the rain that falls originates from the oceans and not from land. So basically most of the rainfall falling originates from the continent. If we would somehow change the evaporation patterns in Europe and Central Asia, they should have a direct effect on the rainfall in China. Finally, in South and Southeast Asia, we do see that continental recycling is important, up to 30%, but less dramatic, if you want, than in, let's say, Africa or Latin America. To highlight the importance of regional moisture recycling, or the effect that we remarked upon in the beginning, namely that recycling is probably, if you just look at a given area, it's scale dependent. You see this nice table here, what they did for Latin America. They just took 1 pixel, in this case 1.5 by 1.5 degree, and they say, okay, what is the precipitation recycling ratio, what's the evaporation recycling ratio? And you see nicely that it starts out very small. If they would have taken a point, this would basically go to 0. But as the area increases, going to doubling and tripling, taking a whole country of Bolivia, the whole Amazonia, and then the whole continent, you see the continuous increase in these recycling ratio, as you would expect, of course. And if you would go to the whole Earth, something you should go to 100. So what you sort of expect is indeed found in the results here as well, which is good. Which then brings them to a nice way of looking at it as well. They say that the continental precipitation multiplier, and it's defined here in equation 24. And basically, it shows like if you would not have any recycling, you would have less rainfall. And actually, basically, how much does this continental recycling then contribute? How much does it multiply the rainfall that you have? And it's an interesting one. And basically, you can see it very nicely in what's happening here. In this global atmospheric water balance. Oh, sorry. Let me go back. What you see is that if we take the precipitation on the continents as 100, that 60% of that comes from evaporation that originated over the ocean. 40% originated from what evaporated over land. Of everything that evaporates from land, which is 70 in this case, 40% comes back as precipitation over the continents, 30% is affected away, and 30% runs off. So this is let's say the global water balance over all continental areas that follows from this model. How does this compare to other known things? Don't forget, they just looked at the atmosphere. They did not look at all at river runoff or something like that. And if they do it this way, they come with a global runoff coefficient of 30, which is significantly lower than what is generally thought to be the case, namely about 40% of the rainfall should run off through the rivers. How do they come at a global runoff coefficient? Well, it's simple. Whatever rains and does not evaporate must run off somehow over the area. So, and they come up at 30%, which is probably somewhat underestimated. Total rainfall, by the way, is fine. It comes. It's very close to what other studies have said. Now, you could of course say, well, apparently there's quite some error in it, but I think when it comes to patterns, general importance of recycling, where it is important, where it's not so important, I think that's still very much smack on. Finally, they also look at seasonal variations of the continental moisture budget, coming with a sort of a summer picture and a winter picture, and it shows that the winter picture, that is the northern hemispheric winter picture, is less dramatic in terms of continental moisture recycling than the summer. In summertime, it's much more important. So that also implies that in drought areas, in periods of drought, which we usually suffer during the summer, this whole recycling things become extra important. So, okay, here are these maps then that you see for the northern hemispheric winter and for the summer. This is the January map. Why you don't see a symmetry there with the southern hemisphere is because there's just relatively little land at mid-latitudes at the southern hemisphere. So that's all. And here you see the summer one. Conclusions. Of course, the conclusions sort of slightly repeat what's being said, but it's important to bring this home. Continental moisture recycling has an important role. China is an extremely striking example of that. They basically completely depend on what evaporates upwind over the continents. And yeah, once you see it, you say, oh yeah, it's all obvious, but we just did not have these images, we did not have these insights before we had this article. It also is important that when you start modeling at large scale, you cannot just say, well, precipitation is it, and we don't care about the evaporation that takes place. No, that evaporation at large scale, evaporation from land has an effect on precipitation on land. Yeah, you see this global multiplier that we talked about before. It's 1.67. So without this taking into account, if you only would take moisture transport from the oceans to the continents into account, you would grossly underestimate the amount of rainfall you would have. You would have to multiply that with 1.67 in order to get at the total rainfall effect. For some reason, it's more significant, this recycling in wet environments in general than in the drier environments. And clearly also, it's like, these maps show where you should be very careful. So please don't cut all the forests in the northern part of Latin America and in Amazonia, because that will have a major effect downwind in the Rio de Plata. Finally, some further research that can be done is like part of these results can be further validated by looking at the isotopic signatures of atmospheric water and rainfall. That's something that still needs to be done, as far as I know. So that's a very good challenge for any of you who would be interested to do follow-up work on this.